Lesson 16.3 is analyzing integrally defined functions. Back to having graphs. Analyzing means we're going to have to think back to the properties we know of when a graph was having negative slope. It was decreasing or increasing, or its concavity, all that kind of stuff. So as number 1 says, the graph of the function f in the figure below consists of line segments and a quarter of a circle. Let g be the function given by g of x equals the antiderivative of -9 to some x value f of t dt. Determine all intervals on the closed interval from -9 to 9 where g is decreasing. So you're thinking, hey, this is the graph of f. This is actually the derivative graph of g. So think that the derivative, think we had g of x. The derivative of that is actually f of x, or f of t. Okay, so we're thinking backwards. Where did we know that the normal function was decreasing? Well, it's going to be decreasing when its derivative, so g prime of x, is negative. Or you could say is less than 0, right? Because if I wanted to graph its derivative, that means the slopes. If the slopes are negative or negative y values, that means that it was decreasing. So if I want to think, okay, I've got this function here, and I'm going to write it first. I want to figure out the derivative. It's kind of like when you solve equations, what you do to one side, you're doing to the other. So now I'm going to take the derivative of this. We talked about a derivative of an antiderivative cancel each other out. So g prime of x is simply going to equal, you plug this in for t, f of x. So I want to know where f of x is negative from -9 to 9. And that would be anytime I'm down here below the x-axis. So I would say from -5 to -2, the original function would have been decreasing, or 3 to 9. So that one's easy. You really could just look at it. Okay, we got a couple more to try. Number 2, it says it consists of line segments and a semicircle. And again, this is f. G is the original function. This again is the derivative graph, so we're thinking backwards. And we're going from -9 to 9. Determine all values of x, if any, where g has a point of inflection. Okay, do you remember points of inflection are where it changes concavity? So if it changes concavity, and I'm looking at the derivative graph, concavity is actually the second derivative. So if I'm looking at the slope of this slope, which I know is confusing, the slope of this slope, because slope of a slope is the second derivative, I'm looking for where is this graph, I'll put f prime, changing from increasing to decreasing, or vice versa. I'll just put arrows. So we're looking at where is this changing. And we just want to go from -1. Ignore that. We don't even have to worry about that. We're looking from -9 to 9. That number is not important to us. But we're also thinking, okay, if I want to know that, I'm thinking, where is g prime of x changing? No, I'm not even going to say that. I think that's going to make it more confusing. Just think about if this is kind of the middle step, if we have the original derivative, then the second derivative, we want to see where are these slopes changing. So that's happening here, because it goes from increasing or positive slope to negative, negative to positive. Even here at the top of the semicircle, it goes from increasing to decreasing, to increasing to decreasing. So there's several values. X would be -4, -1, 1, 3, and 6. All right, number 3, we've got line segments in a semicircle again. we've got g of x is defined by the integral of f of t. Determine where g would have had a relative maximum on the interval -9 to 9. So a maximum, this always helps me to think my slopes had to be increasing and then decreasing to get a max up here. So I need my slopes to go from increasing to decreasing. So g prime of x, if I take d over dx or the derivative of this, it's going to be f of x. Where does f of x go from positive to negative? So we want it to be positive or above the x-axis to below. Positive to negative right here at 6. Okay, and then last one, we're determining where g would have been concave down. Concave down happens when this graph is decreasing. So let's put g is concave down when f, this graph, which is the derivative graph, is decreasing. So it's like the slope of the slope is negative. So it's decreasing here and all of this. And that would be it. So from -9 to -7, or from -5 to 2. Okay, so again, you got to think about concavity is the slope of this slope, so it's where it's decreasing.